Escape velocity is 11.2 kilometers per second. But what if I just kept flying upward at 1 kilometer per hour? Would Earth really stop me? It sounds obvious, doesn't it? If escape velocity is over 11 kilometers every second, then anything slower should eventually fall back. That's what most of us picture. As if Earth has an invisible speed gate surrounding it. Reach the magic number and you're free. Miss it, and gravity pulls you back forever. Except, that's not actually how it works. In fact, if you had the right kind of engine, enough fuel, and an almost unimaginable amount of patience, you really could leave Earth while moving upward at just 1 kilometer per hour. So why does everyone keep talking about escape velocity? The answer turns out to be one of the most misunderstood ideas in all of physics. Let's start with something much simpler than a rocket. Imagine throwing a baseball straight into the air. Throw it gently, and it rises a few meters before falling back. Throw it harder, and it climbs higher. Throw it incredibly hard, and it might even reach the edge of the atmosphere. Every time, the same thing happens. Gravity slows the ball down until eventually it stops rising and begins falling. Now imagine throwing it so unbelievably fast that, even though gravity keeps slowing it down, it never actually reaches zero speed. It just keeps getting farther away forever. That launch speed is what physicists call escape velocity. Notice something important. Nothing magical happened at that exact number. There wasn't an invisible wall, no force field, no cosmic checkpoint. Escape velocity is simply the minimum speed an object needs if you stop pushing it immediately after launch. That's the crucial part. If you stop pushing. The moment your engine keeps working, the entire picture changes. Think about climbing a mountain. You could sprint all the way to the summit in one exhausting burst. Or you could walk slowly, taking one step after another. Either way, you eventually reach the top because you keep supplying energy throughout the climb. Leaving Earth works surprisingly similarly. Gravity isn't asking whether you're moving fast enough. It's asking whether you're still providing enough force to keep climbing. As long as your engine pushes upward harder than gravity pulls downward, you continue gaining altitude, even if you're moving painfully slowly. So why don't rockets do exactly that? Because gravity charges interest. Every second you spend hovering or climbing slowly, gravity keeps pulling on you. Your engines must keep burning fuel simply to avoid falling. That fuel has weight. And carrying more fuel means you need even more fuel just to lift the fuel you're already carrying. It's a vicious cycle. Rocket engineers even have a name for the energy wasted this way. Gravity losses. Imagine carrying a bucket of water uphill with a tiny hole in the bottom. The longer the climb takes, the more water leaks away before you reach the top. A faster climb wastes less. Rockets face exactly the same problem. Every extra minute spent fighting gravity is energy that could have gone toward reaching space instead. Then there's another obstacle: the atmosphere. Near Earth's surface, air is surprisingly thick. Moving through it creates drag, constantly stealing energy. Now imagine crawling upward at walking speed. You'd spend days, maybe weeks, pushing through dense air while your engines burned fuel the entire time. That's an astronomically expensive way to travel. Real rockets solve both problems by accelerating quickly. They punch through the thickest part of the atmosphere in just a few minutes, reducing drag, and they spend less time fighting gravity, reducing gravity losses. In other words, rockets don't accelerate rapidly because physics demands it. They accelerate rapidly because efficiency demands it. Fuel is expensive. Mass is expensive. Every unnecessary second costs energy. The faster you reach space, the less you waste. That also explains something even stranger. Watch almost any rocket launch. After climbing almost straight upward for less than 2 minutes, the rocket begins tipping sideways. At first glance, that seems completely backwards. Nah, if you're trying to leave Earth, why start flying across it? Because most rockets aren't trying to escape Earth at all. They're trying to orbit it. And orbiting has almost nothing to do with getting higher. Instead, it's about moving sideways so fast that while gravity pulls you downward, the ground curves away beneath you at exactly the same rate. You're constantly falling. You just never reach the ground. That's why spacecraft in low Earth orbit travel at nearly 28,000 kilometers per hour. Not because they're escaping Earth, but because they're continually missing it. Escaping Earth usually comes later. Once a spacecraft is already in orbit, it's above almost all of the atmosphere, and it's already moving incredibly fast. Now a relatively short engine burn can add enough energy to stretch its path farther and farther from Earth until it never returns. Notice what's missing. There's no giant leap, no invisible border, no moment when physics suddenly changes, just carefully adding more energy. In fact, many spacecraft don't leave Earth in one dramatic burst at all. Some perform several engine burns spread over hours or even days. Others take an even more ingenious approach. They borrow energy from planets. As a spacecraft flies past a planet, it can steal a tiny fraction of that planet's enormous orbital momentum, leaving the encounter moving much faster than before. This technique, called a gravity assist, lets missions travel far beyond what their fuel alone could achieve. The Voyager spacecraft used this trick to tour the outer planets and eventually leave the solar system altogether. Modern missions often combine multiple engine burns, gravity assists, and years of careful planning. Spaceflight is less like jumping over a fence, and much more like managing an incredibly complicated bank account. Every maneuver is either a deposit or a withdrawal of energy. And that leads to the biggest surprise of all. Escape velocity isn't really about velocity. It's about energy. The famous number, 11.2 kilometers per second, is simply another way of saying, if you launch from Earth's surface and never fire your engine again, this is exactly how much energy you need. Give the spacecraft that energy gradually instead of all at once, and the required speed at any single moment can be much lower. In theory, with an engine that could run forever and enough fuel to keep feeding it, you really could crawl your way into interplanetary space almost as slowly as a person walks. 1 kilometer per hour would be spectacularly impractical. The trip through the atmosphere alone would take weeks, while gravity quietly drained your fuel every second. No engineer would ever design such a mission. But physics itself doesn't forbid it. And that's the part almost everyone gets wrong. Escape velocity isn't a cosmic speed limit. It's simply the minimum speed you need if you plan to stop accelerating immediately. The universe doesn't care how fast you leave Earth. It only cares whether you've supplied enough energy to escape Earth's gravitational pull. What sounded like a simple question about speed turns out to reveal something much deeper. Again and again, the rules that seem absolute are really shortcuts, convenient summaries of more fundamental ideas. And once you understand the hidden trade-offs, one of the most famous numbers in science suddenly makes perfect sense.